Okay, so now looking at exponents and radicals, let's talk about some basic properties and how they're represented. So many of you guys may be familiar already with exponents. It's basically when you have an a to the power b, that's how we say it. So it's basically, if we have it this way, we call this a to the power of b. And the basic properties of these are that if you multiply so if it's b to the x times b to the power y, this is equal to b to the power x plus y. So the numbers on top add up. And similarly, so we have some other properties, which is b anything to the power 0 is equal to 1 unless the number itself is 0. And then we have that b to the negative something is 1 over b to the something. So for example, in this case, is b to the negative x is equal to 1 over b to the x. And we have b to the x divided by b to the y is equal to b to the x minus y. And then we have b to the x to the power y is equal to b to the power xy. We're multiplying x and y. So it's like x times y. And if we have ab to the power x, we can split it up into a to the x times b to the x. So those are exponents. What about radicals? So radicals are nothing but a number to the power like a fraction. So like 1 over n is equal to nth root of it. And this is what we call a radical. This V looking V and then horizontal line looking thing. This is called a radical. And the way we format it is you draw your V thing and then your horizontal line. And then you write the number. So whatever's on the bottom, right? Denominator. And it always has to be 1 over n format. So like if you have something to the power a to the power 2/3, the way you would go about it is say, okay, this is a to the 1/3 squared, or you would call this a squared to the 1/3. And then what you do is you put your a squared inside, and then you put your 3 inside. So that's how you go about writing radicals. It's pretty straightforward, and I'd encourage you guys to do quick exercises on how to move it to radical form and back to fraction form and different things like that. And this can often be useful when you're using the exponent rules, because sometimes when you have to multiply things, for example, something like I'm going to say 4, and this is a to the 3rd, something like that. It's super hard to do it on face because they have different radicals and things. So what you do is you could convert this and be like, okay, this is a to the 2/3 times a to the 3/4. Then I use this rule, and I say this is equal to a to the 2/3 plus 3/4, and that's equal to a to the you take common denominator, so this is equal to 8 over 12 plus 9 over 12, which is equal to 17 over 12. So this is equal to 17 over 12. And then all you do is you just rewrite this as a to the 17 and square root, and then 12th root of that. So that's how you go about writing or using switching between exponent and radical form. So here's a small example about exponents and radicals. So I encourage you to pause here and then try it out on your own, and then we'll just quickly go over the solution. Okay, so let's go into this example. So right off the bat, we're just going to read the question. Suppose that 4 to the x1 is equal to 5, 5 to the x2 is equal to 6, and so on and so forth. And this is equal to 128 over here. So what the question asks is, what is this? And it looks like we're going to have to apply some of our exponent rules in this. So we have 4 to the x1 is equal to 5, and 5 to the x2 is equal to 6. So let's use these two equations to figure out something. So one thing we know is we could replace 4 to the x1 and 5. So we have 4 to the x1, 2 x2. And if you use our rules from bases, and exponent rules, then we get that this is just equal to 4 to the x1, x2 is equal to 6. And now this starts to give us a little hint, because the thing they're asking for us is the product of all the top, or the exponents. So we can just keep plugging this in and it should keep multiplying. And so let's check it out one more time. So we're going to plug this into 6 to the power x3 is equal to 7. So what we're going to do is we're going to plug in 4x1, x2 into this. And you indeed actually get 4 to the x1, x2, x3. So we can continue this pattern, without any flaws, because it seems to be working pretty well. And it should work. So if we keep doing this, we get that 127 when we replace, so replacing 127 with 4 to the x1, x2, so on until x123. We get that 4 to the x1, x2, so on until x123 to the power x124 is equal to 128. And we get that this means that 4 to the x1, x2, all the way till x124 is equal to 128. And then now we just have to figure out which power of 4 works. And so the way we're going to do this is we're going to take this as 2 to the power. So it's 2x1, x2, so on and so forth. x124 is equal to 2 to the power 7, right? 128 is 2 to the power 7, and 4 is 2 to the power 2. And obviously, when you have 2 to the power 2 of y, and this is equal to 2 to the 2y, right, with our rule. So then now we just, all we do is we set the exponents equal. And setting this equal, we get that our answer is actually 7 over 2. So it looks like a weird answer choice. Right by looking at it, you might not think about it, but it is the correct answer choice. And so that's how our exponent rules play into nice AMC problems. And also really simplify things, see how that really collapsed into something really simple. And yeah. So now we're gonna go into absolute value. So going into absolute value, we see that it's not a normal function. Normal functions generally appear to have a set of continuous things that are curvy and nice or straight, and keep going, no sharp turns. But our absolute value is not like that. And also oftentimes our functions have f of x is equal to x. Yay, it's straightforward. So for here, we call this a piecewise function. And what piecewise basically is when different parts, you have to represent it by different functions. And what it is basically, okay, f of x is equal to x if x is greater than or equal to 0, and f of x is equal to negative x if x is less than 0. And this thing is, this combination of these two functions together is what they call the absolute value function, which is represented by a bar and then x and then another bar, closing bar. So the way you actually, when you graph this out, you see that it's a straight line this way and it's a straight line this way. So that's how it looks. It looks quite unusual for a graph. So more clearly. So yeah, but there are definitely properties about the absolute value function that can be really useful. And one of them being that when you square root a square, it becomes the absolute value of x. And partly because if you think about this, okay, I square root 9. Yeah, the common way to write this is 3. But if you realize, actually, both 3 and 3 squared, sorry, negative 3 are 3 squared. Work for square root of 9. So because of that, we have we have this property. And now we have some other properties, which is that an absolute value always has to be positive or 0. And so this is the basic rule that absolute value of x is greater than or equal to 0. There are also some nice ones which are related to multiplication. This one's related to inequality, which is also used in geometry, and we will revisit this when we get into geometry and triangles. This one is nice because what this basically tells is going to the basic definition of absolute value, which is basically measuring the distance from the origin. And so all you do is you draw your nice number line. You have x over here, and you have negative x over here, and 0. So this distance is x, and this distance is x as well. So because of that, the absolute value of x is equal to absolute value of negative x as well. And then we have some other basic ones, which has to do with absolute values and how the solutions are for that in terms of inequalities. And these stuff could basically be found by like a sort of number line. And I think number lines are really useful in this case because you can try out values and see which ones work. And then last but not least, if you have that x is equal to k, we have that x is equal to k over a, or x is equal to negative k over a. So that's about absolute value. So now let's do some quick solves on absolute value. So the first one says that negative absolute value of x is equal to x minus 6. So what we do is we write this as x is equal to 6 minus x. And so now we break this into 2 parts. One where x is greater than 0, and one where x is less than equal to 0. So here we have that x is equal to 6 minus x, which means that x is equal to 3, and so this perfectly works. And then here we have negative x is equal to 6 minus x, which means that if you cancel out the negative x's, you get that 0 is equal to 6, which is not true. So our only value for this is x equal to 3. So now let's do the second one, which has to do with how to operate kind of with these functions. And we're going to use some of the rules that we did before. So obviously we're going to manipulate this equation first by subtracting on both sides. So then we get that 8 times absolute value of 4x is equal to 64. And you divide on both sides by 8, so you get absolute value of 4x is equal to 8. And then now we have to work around this. So recall that we said that absolute value of ax is equal to k would give us that x is equal to k over a or negative k over a. And so what we can do right now is use the same idea because all this would mean is that x is equal to either 8 over 4 or negative 8 over 4, which means that it's either 2 or negative 2. So now we just get that x is equal to plus minus 2. Okay, so I am going to work on the third question now. So these are really quick solves, and I think these are like just to open up your brain with absolute values in general and realizing that there's like 2 different parts to this, a positive and a negative. And so now let's move on to this question. What is the value of x if x minus 1 is equal to x minus 2, absolute value on both sides. So for this one, I think solving it out with all the ranges is just a pain. We're going to go down to the basics, the understanding of absolute value. And what it is it's just a distance from the origin, right? So actually, before we go into that, let's talk about what how we can like deal with this distance. So we know that x, absolute value of x, measures the distance from 0. What if we had something like absolute value of x minus a? And in this case, what it would be is just measuring the distance from A. Point A, you pick a random point A, you're measuring the distance from point A to whatever. Because all you're doing is you're just subtracting and finding the positive value of that. And that's basically what absolute value is, to find the distance of x from A. Is represented here. And obviously, if you plug in a equals 0, you get a normal absolute value. So this is a sort of validation. And now if we use the same idea in our question here, we know that this is just distance from 1 is equal to distance, and this is just equal to distance from 2. And then as a result, this is obviously, since the distance between, since the distance from 1 and the distance from 2 is equal, we get that this is right in between 1 and 2. And that means it's 3/2. So then that's our answer. Pretty straightforward. I'm pretty sure if you went through the steps to do each individual grouping, like ranges and put intervals down and then figure out which values work and things, it would take a long time. And this really works out in that sense. Okay. And so now let's do a couple more quick solves on it.